Here's the question. It's relatively compact, relatively short and sweet. It's broken down quite nicely for us into 3 separate parts, and each part is only worth 1 or 2 marks each. So that's an indication that it should be a fairly straightforward question requiring not too much work. In any case, as always, you should read through the question 3 times before you start it. It's a standard thing that the examiner isn't going to tell us what the question is about. There isn't like a heading for each question on the paper telling you this is a question about this topic from the syllabus or that topic from the syllabus. It's for you to determine what topic or topics are covered by this question. So a standard way of doing this is to have a browse through it at the very least. See if you can pick out some keywords. Here's the first one that stands out to me. At some point we're being asked to sketch a graph. Okay, so I'm immediately thinking of graphs and functions. In part B, here's a keyword that only A-level mathematics students would understand, and that's logarithm or logarithms. So that's definitely going to come into the question. If I don't know what a logarithm is, I'm not going to be able to access the marks from part B at the very least. And again, something a bit more familiar in part B. I'm going to be asked to solve an equation. I mean, the phrase solving an equation is familiar from GCSE study, but presumably the equation that's going to crop up here would be something a bit more advanced than I would come across in GCSE maths. There are a couple of other key features of mathematical content within the question, but they're coded into the question in such a way that no obvious keywords pop out at me. So we'll have to deal with those as we come across them. As always, we should approach questions in exactly the order that the examiner is suggesting to us. Even if you have read through parts A, B and C, please make sure you start with part A, focus on that and answer exactly what is asked of you in part A. So let's start with part A. Very clearly, I'm being able to sketch the graph of a particular function. It is absolutely essential that we recognize what type of function we are dealing with here. So I'll give you a couple of seconds to think about that. You need to know the name of that type of function. The type of function that's being indicated is an exponential function. Exponential functions have the form y equals a to the power x, where a is some specified constant numerical value. A will always be a positive value. A is called the base of the exponential function. Now you may have looked at the question and yeah, I get that. I understand this is an exponential function. That's completely obvious. But one of the standard pitfalls here is that students from time to time confuse exponential functions with power functions. Power functions have the form y equals x to the power of a, where a is a specified numerical constant. In this case, a might be positive or negative, actually. Okay, you can see just from the way I've written it side by side there, it would be, if I'm really careless or under the pressure of exam conditions or whatever, it would be relatively easy to confuse these two things. And what's worse is that, in some respects, the graphs of these two functions have certain similarities. And the examiner will need us to demonstrate that we understand in what ways the graphs of these two functions are different from each other. Okay, so we're definitely looking at exponential functions here. When asked to sketch a graph, there's certain key things you need to do and certain things that you don't need to do and shouldn't do. So for starters, you need to draw a pair of axes. Axes are just straight lines with arrowheads at one end. A little bit of familiarity with exponential functions should indicate to you that the axes I need are like this. I'll just put the labels on the axes before I forget. X and Y, you must do that even for a sketch graph. So you can see from what I've drawn here is I need both the positive and the negative parts of the x-axis, but I only need the positive part of the y-axis. It's my knowledge of exponential functions that has indicated that to me. Another tiny detail, you'll notice I put arrowheads at one end of each axis. Sometimes some students, and even in some textbooks and even online sources, you'll see that sometimes people put arrowheads on both ends of their axes. That's not really correct. The arrowhead is indicating the direction in which that variable increases. So x increases from left to right along the horizontal axis, and y increases upwards along the vertical axis. I think we're now ready to sketch in the graph. You'll notice that I'm not going to put any numerical values on the axes. Again, students sometimes spend some time with their ruler marking out, neatly marking out x and y values along their axes. So marking a numerical scale on each axis. And they sometimes maybe do a table of values. You're not expected to do that here, and you shouldn't really do that. It will take too much time and it will cause too much confusion. The examiner would like you to demonstrate that you understand the basic shape of the graph. So at this stage, having drawn the axes and labelled them just with the x and the y, you need to sketch in the general shape of the graph. It should look like this. Okay, it curves upwards. I'll come back to some of the main details of the graph. Before you do anything else, I would strongly advise you to label the graph like this with the equation of the graph. That's not so important in this question, but in other questions you're quite often asked to draw different graphs on the same axes. In that case, if you did not label your different graphs, the examiner would have no way of telling which one you think is which. So always, 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 when drawing or sketching graphs, label your graphs. So what I've got there is the bare sort of minimum details. Now they ask me for one particular detail on the graph. They ask me to indicate the value of the intercept on the y-axis. Well, the intercept on the y-axis, that's when x has the value 0. So in that case, from the formula there, y equals 9 to the power x, y would have the value 9 to the power 0. And anything to the power 0 is, of course, 1. Exponential graphs like this always cross the y-axis at the value 1. So here's some more basic features of the graph. Firstly, the graph only exists in the first and second quadrants of the xy plane. So the graph only exists for positive values of y. Another way of saying that, the graph exists in the upper half plane. You will note that the graph does not touch or intersect the x-axis. You need to show that very clearly. If you tend to be a little bit scruffy with these things, and if it looks like your graph is touching the x-axis, you can expect to lose a mark there. The other thing about the shape of the graph, I mentioned that it was curved. The gradient is always positive, so reading from left to right, the graph is always going uphill, and the gradient's always increasing going from left to right. So the gradient is it's getting steeper and steeper and steeper reading from left to right. So again, if you were to draw this a little bit carelessly, and you had the graph sort of curving in the wrong direction, so at some point going on the left-hand side there, for example, curving backwards, curving upwards, reading from right to left, then you can expect to lose a mark. That's not the shape. And in fact, it would look to the examiner like you've drawn something more like a power function in that case, rather than an exponential function. Okay, so pay careful attention to where the graph is in relation to the axes and what the general trend, the general shape, the gradients of the graph are. A couple more specific details. I mentioned that the graph does not intersect or touch the x-axis, but what you should know is, as I go further and further to the left, the graph gets closer and closer to the x-axis. So we can say the graph asymptotes to the x-axis over on that side. It's a little bit hard to indicate that You see, even on my graph, it looks towards the end as if my graph is actually parallel to the x-axis. But you need to give some indication. In some other types of variations of this question, you'll get an extra mark for indicating that asymptotic nature of the graph. And then by contrast, over on the right-hand side of the graph is getting higher and higher. That means larger and larger y values and steeper and steeper. So my graph has to reflect that. Again, it looks like my graph's got a little bit straight there because of the way I've drawn it on this software, but it should definitely be curving. And that's it. That's enough detail for 2 marks. And I've also mentioned a few details which we weren't asked for, but like I said, in other questions, sometimes we're asked for a bit more detail than we were in this question. Let's move on to part B, which is significantly different from part A. As referenced before, part B contains this keyword logarithms, and it also makes it very clear that I'm being expected to solve an equation. This type of equation is called an exponential equation. As in part A, the examiner has not used the word exponential. It's for me to know, and to know that and to understand the significance of that term. The equation I'm given is essentially based on this relationship. Now, admittedly, the equation only has an x, it doesn't have a y. What I've done here, again, like from I've tried to make a link with part A of the question, step 1. I've written down the general expression for an exponential function. What you need to show an awareness of is how exponentials relate to logarithms. So I'm taking this back a step here, and we need to know this basic fact. The statement I've got on that line there, this formula, if you like, or equation, this exponential relationship between x and y, is equivalent to this logarithmic relationship between x and y. Take a careful look at this, just in case you're not familiar. That little double arrow in the center simply means is equivalent to. The statement on the left is equivalent to the statement on the right. The double-headed arrow is also sometimes referred to as if and only if. So the context there is if the statement on the left is true, then the statement on the right is true. And also if the statement on the right is true, then the statement on the left is true. The double-headed arrow can also be described as implies and is implied by. So the left-hand statement implies the right-hand statement, and the right-hand statement implies the left-hand statement. What I've got written on the screen there, that single line there, explains what logarithms are. It's a definition of what a logarithm is. So on the right, I've used logarithm to the base a. On the left, in the exponential statement, the base of the exponential there is a, and that then plays the role of the base for the logarithmic statement on the right. You'll notice it's the x and the y that are swapped around. The a is called the base in both cases. Again, if you're a little bit shaky on this, students tend to get the positions of these various letters mixed up. And the way to think of it is this. Think of a, the base, as a fixed positive number. That's why in common usage, in common with textbooks and so on, I've used a letter from the beginning of the alphabet to indicate a constant, and think of x and y as variables. Then each of these relationships here is a functional relationship between the two variables. Okay, there's lots more we could say about logarithms and exponentials, but this is just a 2-mark question, so let's crack on with it for now. In our case, looking at the equation given in the question, it matches to the exponential statement on the left here, and it's very clear that the base of the exponential is 9, and that y has the numerical value 15. So here's the equation I'm given in the question. So on the basis of the line immediately above, this is equivalent to the logarithmic statement x equals log to the base 9 of 15. And that's it. That's how simple this question is. That is the value of x in exact terms. Now, of course, that doesn't really help me very much. I need my calculator to give a numerical value, and the examiner is hinting at that by asking me to give the answer to 3 significant figures. So you need to find the general logarithm button on your calculator. You need to enter in log to the base 9 of 15, and your calculator should give you this awkward decimal. You're then asked to round to 3 significant figures. You've got a couple of ways of doing that, please don't forget. You can do it by hand yourself to get x equals 1.23. Or you can use one of the settings on your calculator to give all decimal outputs to 3 significant figures. Even the older versions, the much older versions of the Casio calculators, have the facility for the calculator to give all decimal answers either to a certain number of decimal places or to a certain number of significant figures. If you weren't aware of that, please go away and have a play around with your calculator to find out about that facility. It's really useful, and even at GCSE, that little facility is, can buy you a few marks in an exam and can save you some losing marks due to really careless errors. Okay, before we move on, let's just review this answer, make sure it makes sense. We're getting that x is 1.23. Look again at the equation given to us at the top of the screen. What this is suggesting is that 9 to the power of 1.23 or thereabouts is 15. Is that reasonable? Well, 9 to the power of 1 would be 9. And 9 to the power of 2, 9 squared, would be 81. So 9 to the power of 1.23 would definitely be in between 9 and 81, which 15 definitely is. And again, just in the sort of very rough and ready fashion, 15 is significantly closer to 9 than it is to 81. So, yeah, we would imagine the solution of this equation should be x is 1 and a bit. And that's how it's turned out. So that looks about right. Let's move on to part C of the question. Part C is rather suspiciously only worth 1 mark. That means there should only be really one thing for us to do. But again, it's one of these questions whereby it's relatively a lot of work for 1 mark, I think. But there you go. Let's go back to the graph. We don't have to do this, but I think there's a hint in the question. It says the curve is reflected in the y-axis. Given that we took the trouble in part A to sketch a nice neat graph, wouldn't it be sensible to make use of this? So here's my graph again. Again, look, I've labelled the graph, and this is one of those occasions where I'm going to have another graph on the same axis, so labelling the graph is definitely smart. In the exam, of course, you wouldn't have to draw out the graph again. You could go back and use the previous graph that you've drawn. Okay, I'm now going to reflect this curve in the y-axis. So think carefully about what that would look like. Imagine putting a mirror along the y-axis. Some students can do this straight off and perfectly comfortable. Some people like to use tracing paper. It's entirely up to you. But it should occur to you, when I reflect a curve in the y-axis, the point at which the curve crosses the y-axis remains fixed. That's the fixed point of what we call this transformation. You should get this. Remember that in the exam you're not allowed to use colours. I've used a couple of different colours for the graphs. So in the exam you would have to draw the reflection. Well, you wouldn't have to as long as you label everything, but it might not be a bad idea to draw the reflection as a dashed or dotted graph. Okay, let's have a look at that reflection in more detail. Reflection is what we sometimes call a point transformation. Each point on the original graph is being reflected in the y-axis. Let's just pick one of those points at random. So this point has whatever x value and whatever y value. I can't read them off my axes because I didn't draw numbers on my axes. But where would this point map to under this reflection? Well, presumably you can see, again, drawing roughly by hand, it would map to over there, wouldn't it? Okay, so what has actually happened in terms of coordinates to go from the blue point on the right, on the original graph, the original curve, to the reflected green point on the left on the reflected curve? Well, it should be clear to you that the y coordinate has not changed, but the x coordinate has changed sign. So y remains the same and x has been replaced by negative x. And that would be the same for each point on the original graph. Its reflection would be the corresponding point on the reflected graph where the value of x has been reversed, has been negated. So that gives me a really easy way to answer the question. Again, look at the top right in blue, how I've labelled my original curve. The equation or formula was y equals 9 to the power x. I've just suggested that the values of y don't change and the values of x are reversed, they're negated. So the equation formula describing the new graph should be this. So y remains the same and x has been replaced by negative x. So the equation for the curve is y equals 9 to the power negative x. The way the question is phrased, they would prefer me to write that using function notation, so replacing y with f bracket x. I'll put it down the bottom of the screen here. The function they are asking for is f of x equals 9 to the power of negative x. And that's it. That will be enough for my 1 mark. I'm just going to offer you one more thing with this part of the question. Provided that you're proficient with indices, you should know that an equivalent expression for this function would be 1/9 to the power of x. That might be relevant in other questions because you should know that the graph of an exponential function, a to the power x, will only be increasing if the base a is greater than 1. If the base a is less than 1, for example 1/9, then the graph will have this decreasing shape as shown by the green dashed curve here.
There's a mention in this question about the difference between exponential functions and power functions. Now, power functions are functions of the form x to the n, where n is a positive integer. And so we start off with x to the 1, which is just x, so we've just got y equals x. And then we have x squared, which is familiar, as it's symmetrical in the y-axis, x cubed, cubic, which is rotationally symmetrical by 180 degrees around 0, and then the 4th power quartic, which is symmetrical again. So the even powers are symmetrical in the y-axis, and the odd powers, we go up to the power 5, are rotationally symmetrical around 0. And we call the ones that are symmetrical in the y-axis are called even functions, and the ones that are rotationally symmetrical around 0 are called odd functions. And you might like to reflect on that in relation to trigonometrical functions. So that's our power functions. Exponential functions, and these are a number to the power of x. So with the power functions, the number was the power and had to be an integer, a positive integer. For the exponential functions, it could be any number there. And what we can see is that if we go below 1, then we have a curve that comes from infinity downwards and then tends towards 0. and then as we go up into the positive, it flips round and they tend towards 0 as we go to negative infinity and go up towards infinity that way. So in terms of the shapes of the functions, the exponential function either comes from 0 and shoots up, going through 1 every time. You can see that as we reduce the number, the exponent, or it's negative, it comes from infinity down through 1. Now, of course, that number 1, if this is times by something, if we had 3 times 0.7 to the power of x, it would cross at 3. But without that multiplier, it always crosses 1. And it's never symmetrical. Whereas the power functions are either evenly symmetrical or oddly symmetrical. Now, there is another function that won't come up in your A-level studies, but it's a weird one. So that's x to the power of x. You'll notice that dips down at the beginning. It's between 0 and 1, and you can have a ponder about that yourself. So what might be interesting is to see what's happening up here off the screen. So now we've got the power function is at 5, so we've got x to the power of 5, we've got 5 to the power of x, and then we've got x to the power of x. So if we zoom that in a bit more, so we get our 5 coming into our scale, pop it in there, then it's difficult to tell what's happening, but what we can do is squeeze it down. So if we do it 1 to 10, we can see that the blue line, the power function, is still ahead before we get to 5, and the green is next, and x to the power of x is lagging behind. And squeeze it down some more, let's see what happens. So again, until we get up to 5, certainly the exponential function is climbing more slowly than the power function. If we go down a lot more, we can see that something interesting happens at 5. What happens is everything swaps round. And if you think about the way that these three functions would work, once we get past 5, then the fact that they swap round at this point will make sense. So have a little think about that on your own. And you can set this up easily enough on Geogebra for yourselves if you fancy having a look. So I'll leave you there.
Let's review the core skills that we needed to answer that question. First and foremost, the question was mostly about exponential functions, and one of the puzzles of the question was that the examiner managed to phrase the question without using the word exponential. Whether that was a deliberate ploy, I'm not quite sure, but you can expect the examiners to test your understanding of various things and how things link together. And like I said before, the examiner is not going to spell out to you what a question is about. That's for you to determine by reading through the question. And the key things here that we needed to know about exponential functions were certain properties of the function and what graphs of exponential functions tend to look like. Now, I've been a bit vague there in saying properties of exponential functions, but one of the purposes of graphs is to, in some way, illustrate properties of functions. Once I know what the graph of a function looks like, then I've got a pretty good understanding of lots of properties of the function. And that's why, going way back to GCSE, you've been asked to sketch various graphs of all sorts of functions, so exponential functions, power functions, and all sorts of other functions. By getting to know the features of the graph, that helps you to understand the properties of the function. The other key component in relation to exponential functions was, of course, logarithms. You need to understand, remember in part B of the question, you need to understand the key relationship between logarithms and exponentials. You need to learn that relationship, and of course you need to understand how to use and to apply it in various situations. In particular, in this question we used that relationship to solve an exponential equation. You can expect to be asked to solve significantly harder exponential equations than the one that we saw here in part B. So make sure you look at a few practice questions, go back over various other past paper questions and practice questions, and dig out some harder exponential equations and see if you can solve them. The other component, again a nice link with GCSE maths, the part C involved transformations of graphs and functions. So these are two related things. When you first learn about transformations, you learn about transformations of shapes. Only much later on, right at the sharp end of GCSE, do you learn about transformations of graphs and transformations of functions. Remember, as I was hinting at before, a graph is just a certain representation of a function. So a transformation of a graph is in a way a proxy for a transformation of the function itself. And lastly, you may think this wasn't necessary to know this for this particular question, but I showed you right at the end of part C. I was claiming it was useful to know something about rules for indices. So why is that 9 to the power negative x is the same as 1/9 to the power of x? You should be aware of those things, and of course that could easily be worked into a trickier question on this topic. Let's take a quick look at just a couple of wider links arising from this question. Exponential functions are often used in modelling situations. This cropped up very briefly in GCSE maths, and it crops in a few different places in both the pure and the applied units of A level. So for example, growing exponential functions such as 9 to the power x are used to model things like population growth, and decaying exponential functions like 9 to the power negative x can be used to model radioactive decay, and also modelling Newton's law of cooling, I think is the other standard example from A-level maths. Again, those who are doing physics should be pretty familiar with those kind of things. And the other obvious thing that didn't crop up in this question was a bit more detail about logarithmic functions. In other questions, we will be asked to sketch graphs of logarithm functions, and possibly to do other things such as to transform graphs of logarithm functions.